Consider for a moment what we are actually doing when we drink a glass of milk. We are consuming a substance produced by the mammary glands of another species, specifically designed to nourish the offspring of that species during the first weeks or months of their lives, before they are capable of eating solid food. Every mammal on Earth produces milk for its young, but no mammal on Earth other than humans continues to drink milk after weaning. And no mammal on Earth other than humans drinks the milk of a different species at all. We do both. We drink cow's milk as adults, and we have been doing so for approximately 10,000 years. And in that 10,000 years, a genetic mutation that allows adults to digest lactose, which is the primary sugar in milk, has spread through certain human populations with a speed that geneticists describe as one of the strongest signals of natural selection in the entire human genome. Milk changed us. Genetically, literally. A food altered the human species to be able to consume it more efficiently, because the population that could consume it had a survival advantage significant enough to propagate the trait across generations. That is not a minor thing. That is one of the most dramatic examples of gene culture co-development in human history. Today, we begin a 4-part series on dairy. And we begin where everything in dairy begins, with milk. This is Eat or Die, Stories from the Human Table, from Renegade Health Group. I'm Zach Sykes. Last week, we covered probiotics, the fermented food bridge that connects everything we've discussed about the gut microbiome to what's coming next. Today, we begin the dairy series, 4 episodes on milk, butter, yogurt, and cheese. Each one builds on the last. Each one is a distinct story that happens to share an origin. That origin is a cow. Or more precisely, a wild aurochs, the massive ancestor of modern cattle, standing in a field in what is now Turkey or the Middle East, approximately 10,000 years ago, and a human being making a decision that would alter the nutritional landscape of half the world. Let's begin. Milk is a complete food in the most literal sense. It is designed to be the sole nutrition source for a rapidly growing mammal. It contains everything a newborn calf needs: carbohydrates, protein, fat, vitamins, minerals, water, and a remarkable array of bioactive compounds, including hormones, growth factors, antibodies, and enzymes. Nutritionally, whole cow's milk contains approximately 3.2% protein, primarily casein, which makes up about 80% of milk protein, and whey, which makes up the remaining 20%. It contains approximately 3.5 to 4% fat, a mix of saturated, monounsaturated, and a small amount of polyunsaturated fatty acids, including conjugated linoleic acid, or CLA, which has some documented metabolic benefits. It contains approximately 4.5 to 5% lactose, the milk sugar that is central to the entire lactase persistence story. And it is one of the richest dietary sources of calcium, phosphorus, iodine, vitamin B12, riboflavin, and potassium. Milk comes from cows primarily in the modern industrial system, but across human history and across the world, It has come from goats, sheep, water buffalo, yaks, camels, horses, and reindeer. The nutritional profile differs meaningfully by species. Goat milk has smaller fat globules and slightly different casein structure than cow milk, making it more digestible for some people. Buffalo milk, used in traditional Italian mozzarella, is richer in fat and protein than cow milk. Each species produced a milk adapted to its own offspring's needs, and humans have made use of all of them. The species distinctions will matter when we get to the A1 versus A2 protein conversation. Keep them in mind. The wild aurochs, Bos primigenius, was one of the most formidable animals in the ancient world. Standing nearly 2 meters at the shoulder, with massive forward curving horns, it roamed the grasslands and forests of Europe, Asia, and North Africa in enormous herds. Julius Caesar described it in his Gallic Wars as only slightly smaller than an elephant in ferocity and speed. The domestication of the aurochs into what we now call cattle began approximately 10,000 years ago, most likely in the Fertile Crescent, the same region where grain agriculture was developing simultaneously. The initial motivation was almost certainly meat and labor, cattle as food animals and as draft animals for agricultural work. Milk came later. The earliest evidence of dairy processing, which was ceramic vessels with milk fat residue, dates to approximately 7,000 to 8,000 years ago in the Middle East and southeastern Europe. By this point, humans had been keeping cattle for several generations. And someone, we will never know who, first observed that the milk these animals produced for their calves could be consumed by humans as well. And not just consumed. It could be processed into butter and cheese, extending its shelf life and concentrating its nutrition. Now, here is the biological problem with that observation. Virtually all adult mammals, including early adult humans, stop producing the enzyme lactase after weaning. Lactase is what breaks down lactose, the primary sugar in milk, into glucose and galactose that the gut can absorb. Without lactase, lactose passes undigested into the large intestine, where gut bacteria ferment it, producing gas, bloating, cramping, and diarrhea. The condition is today called lactose intolerance, and it is not a disorder. It is the biological default for adult mammals. Tolerating lactose as an adult is the mutation. Sometime between 5,000 and 10,000 years ago, geneticists debate the precise timing and location. This mutation occurred in a human population in either the Middle East, the Pontic steppe of Central Eurasia, or possibly independently in East Africa. The mutation was in a regulatory region near the LCT gene, the gene encoding lactase, and it caused the gene to remain active in adulthood rather than switching off after weaning. This mutation is called lactase persistence, and in the populations where it arose, it spread with extraordinary speed. How extraordinary? Geneticists measure the strength of natural selection on a scale where most advantageous traits spread slowly over many thousands of generations. The lactase persistence mutation in European populations shows a selection coefficient, or the measure of the reproductive advantage it conferred, that places it among the strongest selective sweeps ever identified in the human genome. Stronger than most disease resistance mutations. Why was the advantage so strong? The leading hypothesis is straightforward and compelling. In the environments where the mutation arose and spread, populations were keeping cattle. The cattle produced milk, and the people who could digest that milk as adults had access to a reliable, high calorie, high protein, calcium rich food source year round. In environments with periodic famine, with limited alternative food sources, with the constant threat of starvation, being able to drink milk was a survival advantage significant enough to propagate the trait through a population within a few thousand years. Now, the mutation did not spread everywhere. Today, lactase persistent rates vary enormously by ancestry. Approximately 90 to 95% of people of Northern European descent carry the trait and can digest lactose as adults. Among East Asian populations, the rate is only 10 to 15%. Among West African populations, it can vary widely. Some groups that have historically kept cattle have moderate rates, others do not. And among indigenous American populations, it is remarkably low. The global map of lactase persistence is, with remarkable precision, a map of which human populations have historically kept dairy cattle. The gene followed the cows, or more precisely, the people who could use the cows most efficiently, and then pass the gene to their children. This is gene culture co-development, a cultural practice creating selective pressure that altered the human genome in the populations that practiced it. It is one of the clearest and most dramatic examples of this process in the entire human record. And it happened in human development terms essentially yesterday. With lactase persistence spreading through cattle-keeping populations, dairy became a nutritional and economic cornerstone of Old World civilizations in ways that shaped culture, cuisine, and survival for millennia. In the ancient Middle East, dairy was central to the pastoral economy. The Bible describes Canaan as a land flowing with milk and honey, an image of agricultural abundance that resonates precisely because milk was abundance, in a world where reliable nutrition was never guaranteed. The Epic of Gilgamesh, one of the oldest surviving works of literature, describes the wild man Enkidu being civilized partly through the consumption of bread and dairy. Civilization and dairy were, in the ancient Near Eastern imagination, very connected. Across the steppes of Central Eurasia, the vast grasslands stretching from Hungary to Mongolia, the pastoral nomads who dominated the landscape for thousands of years built their economies and their diets almost entirely around their herds. The Scythians, the Huns, the Mongols, all pastoral peoples for whom fermented mare's milk, kumis, was a dietary staple, a ritual drink, and a trade commodity all at once. Genghis Khan's armies reportedly subsisted largely on dried meat and fermented milk when they were on campaign. A nutrient-dense, portable, non-perishable combination that supported military movements across thousands of miles. In Northern Europe, where the combination of limited sunlight, poor growing condition for crops, and high lactase persistence rates made dairy especially valuable, cattle became the primary measure of wealth. Cattle were currency. Milk was money. The industrialization of milk production in the 19th century created a public health crisis before it created a solution. As cities grew and urban populations expanded far beyond what local agricultural land could support, dairy operations moved closer to cities and grew in scale. Urban dairies in the mid 19th century were, by any modern standard, catastrophic environments. Cows kept in dense, filthy conditions, often fed on distillery slop or other industrial waste, producing milk that was frequently contaminated with bovine tuberculosis, typhoid fever, scarlet fever, and a range of other bacterial pathogens. Infant mortality in 19th century cities was appalling. A significant proportion of that mortality was milk related. Studies in New York City in the 1880s and 1890s documented that milk from urban dairies was a primary vector for childhood mortality from infectious disease. Reformers called it swill milk. They were not wrong. Louis Pasteur had demonstrated in 1864 that heat treatment could kill microorganisms in wine and beer without destroying the product. The application of this principle to milk, pasteurization, was developed and advocated through the late 19th century and began to be implemented in American and European cities in the early 20th. The results were immediate and dramatic. Infant mortality from milk-borne disease plummeted. Tuberculosis transmission via milk declined sharply. Pasteurization is one of the clearest public health victories in the history of food safety. This history matters for the current moment, because the raw milk movement, which has grown in visibility in recent years, operates as though pasteurization is a modern conspiracy rather than a hard-won public health achievement. Let's be direct. The epidemiological record on raw milk is not ambiguous. Raw milk is up to 840 times more likely to cause foodborne illness outbreaks than pasteurized milk, according to the data. The pathogens it can carry, the E. coli, the Salmonella, the Listeria, Campylobacter, they are capable of causing serious illness, organ failure, and death, particularly in children, the elderly, pregnant women, and immunocompromised individuals. The claimed benefits of raw milk, superior nutrition, beneficial enzymes, probiotic content, those do not hold up to scrutiny. The heat used in standard pasteurization does not meaningfully reduce milk's vitamin content. The enzymes in raw milk that everyone loves are primarily bovine digestive enzymes that have no demonstrated benefit in human physiology. The probiotic bacteria in the raw milk are not the beneficial strains for humans. Pasteurization saves lives. It saved them in 1910. It saves them now. And that is the position of this show, and it is the position supported by a century of public health evidence. The professor is in, and the professor is genuinely glad that we've already covered that raw milk nonsense. 2 mechanisms today. One settled, one emerging. We'll be clear about which is which. Lactose is a disaccharide, a double sugar composed of one glucose molecule bonded to one galactose molecule. It is the primary carbohydrate in mammalian milk, present at approximately 4.5 to 5% concentration in cow's milk. To absorb lactose, your small intestine must first split that bond. The enzyme that does this is lactase, produced by the cells lining the small intestine. In infants, lactase production is high. In most mammals, including most humans, lactase production declines sharply after weaning, typically beginning in early childhood and reaching low levels by adolescence. When lactase is absent or insufficient, undigested lactose passes into the large intestine. There, the resident gut bacteria ferment it enthusiastically. The products of that fermentation are gas, organic acids, uncomfortable. The gas causes bloating, cramping, and flatulence. The organic acids draw water into the colon osmotically, causing diarrhea. The severity varies by individual, by the amount of lactose consumed, and by the specific composition of the gut microbiome. Some lactose intolerant individuals can consume moderate amounts of dairy, particularly if it's fermented dairy, where bacteria have already broken down much of the lactose, with minimal symptoms. Others react strongly to even small amounts. Approximately 65 to 70% of the global adult population has reduced lactase activity. That is the biological majority. Lactose intolerance is not a disorder. It is the ancestral base condition. Lactase persistence, the ability to digest lactose as an adult, is the mutation, the derived trait, the exception. Understanding this reframes the entire dairy conversation. Dairy is not universally appropriate for all humans, and the populations for whom it is most appropriate are those whose ancestors were dairy farmers for thousands of years. Now for the emerging science. The professor presents this as what it is: a plausible, accumulating, not yet settled body of research that is worth understanding and worth watching. So casein makes up approximately 80% of milk protein. The dominant form of casein in cow's milk is beta casein, and beta casein comes in two main genetic variants, A1 and A2. The A2 variant is the ancestral form. It's the version found in the milk of goats, sheep, buffalo, and most non-European cattle breeds, as well as in human breast milk. The A1 variant is a mutation that arose in European cattle herds, specifically in the Holstein and Friesian breeds that dominate commercial dairy production in the United States, United Kingdom, and much of the industrialized world. Most commercial cow's milk in Western countries is predominantly this A1 variant beta casein, or a mixture of the A1 and A2. Why does this matter? Stay with me here. When A1 beta casein is digested, it releases a peptide or protein fragment called BCM7. BCM7 is an opioid peptide. It binds weakly to opioid receptors in the gut and maybe in the brain. In the gut, BCM7 slows transit time and has been proposed to contribute to digestive discomfort that some people experience with cow's milk. Discomfort that is distinct from lactose intolerance and is not resolved by lactase enzyme supplements. A2 beta casein does not release the BCM7 upon digestion. Its protein structure at the relevant cleavage point is different. Only a single amino acid change, proline instead of histidine, prevents that BCM7 fragment from being released. Several randomized control trials have now compared A1 and A2 milk consumption in lactose intolerant and dairy sensitive individuals. The 2019 study, published in the European Journal of Clinical Nutrition, found that A2 milk consumption produced significantly less digestive discomfort, less bloating, and less stool frequency than the conventional A1-A2 mixed milk in adults with self-reported dairy sensitivity. A 2020 study found similar results in Chinese adults, a population with very low lactase persistence rates. The research is real, consistent in direction, but not yet large enough to be definitive. What it does suggest is that some, possibly more than some, people who believe they are lactose intolerant may actually only be responding to that A1 beta casein and BCM7 rather than to lactose itself. If you have digestive trouble with conventional dairy but have not tried A2 milk, it's definitely an experiment worth running. A2 milk from cows that carry only the A2 gene is now commercially available. It is more expensive than conventional milk, but you can also get that A2 from goat milk, sheep milk, and buffalo milk. And it may explain why some people who cannot tolerate cow's milk do well with these alternatives. So, what do we do with all this information? 3 practical positions. All 3 are direct. Position 1: drink whole milk. The low fat and skim milk recommendation, dominant in American dietary guidelines from the 1970s through the 2010s, was a product of the same low fat dietary era we discussed in the sugar episode. It has not held up. The fat in whole milk is not the villain it was made out to be. Milk fat contains a mix of saturated fatty acids, some neutral, some potentially beneficial, as well as conjugated linoleic acid, which has documented anti-inflammatory and body composition benefits in animal and some human studies. It contains fat-soluble vitamins A, D, E, and K2 that are present in whole milk but absent or dramatically reduced in skim. Critically, multiple large prospective studies have failed to find any association between whole milk consumption and increased cardiovascular disease risk. 2017 Lancet study of 130,000 people across 21 countries found that full-fat dairy consumption was associated with lower risk of cardiovascular disease and mortality, not higher. A meta-analysis published in the American Journal of Clinical Nutrition in 2021 found no significant association between full-fat dairy consumption and cardiovascular events. Skim milk removes the fat, and with it, the fat-soluble vitamins, the CLA, and the satiety signal, the feeling of fullness that fat provides and that moderates total calorie consumption. What remains is protein, lactose, and calcium in a less satisfying, less nutritionally complete package. Drink whole milk. If calorie density is a concern, drink less of it, not a skim version of it. The rule? Whole milk. Full fat, always. If calories are a concern, reduce quantity, not fat content. Position 2. Try the A2 if you have dairy sensitivity. If you experience bloating, cramping, or digestive discomfort with conventional cow's milk, and particularly if lactase enzyme supplements don't fully resolve the problem, the A1 versus A2 distinction is worth exploring. A2 milk is available at most major grocery chains today, typically at a price premium 30 to 50% above conventional milk. The experiment is simple. Eliminate conventional cow's milk for 2 weeks. Substitute the A2 milk in the same quantities and preparations, and monitor your symptoms. If they improve significantly, you're likely responding to the A1 beta casein rather than to the lactose. Alternatively, try goat milk or sheep's milk, both naturally A2 and both widely available, and both with slightly different fat globule structures that some people find more digestible than cow milk, regardless of the casein variant question. If A2 milk also causes significant discomfort, lactose is likely the primary driver. In that case, fermented dairy, yogurt, and kefir, which we covered in episode 13, is the most practical solution. The fermentation process breaks down the majority of the lactose before you consume it, making these products tolerable for many lactose intolerant individuals. Position 3. Skip the raw milk. The raw milk movement has grown in visibility and cultural cachet in recent years, particularly in communities that prioritize natural and traditional foods. The instinct toward less processed is generally sound. Applied to raw milk, it is not. The pathogens that pasteurization kills, E. coli 0157H7, Salmonella, Listeria, Campylobacter, these are not rendered harmless by the fact that the milk comes from a small, grass-fed, well-managed herd. A healthy-looking cow can shed that E. coli asymptomatically. Campylobacter is present in a significant percentage of raw milk samples, even from farms with excellent hygiene. The CDC data on raw milk outbreak rates, 150 to 840 times higher per unit, reflect not individual farm quality, but the fundamental microbiological reality of an unsterilized animal product. The nutritional benefits claimed for raw milk are not supported by the evidence. Pasteurization at standard temperatures does not meaningfully reduce the content of calcium, protein, or most vitamins. It does reduce vitamin C slightly, but no one is drinking milk for the vitamin C. The beneficial enzymes claimed for raw milk, they're bovine enzymes that function in bovine physiology and are not demonstrated to have any human health benefits. If you want the full nutritional profile of dairy with minimal processing, buy pasteurized whole milk from grass-fed cows. You get the fat-soluble vitamins, the protein, the CLA, everything the raw milk advocates are seeking, without the pathogen risk. That is the rational position. 10,000 years ago, someone in the ancient Near East made a decision to keep a wild aurochs alive past the point where it would have been slaughtered for meat, to keep it for its milk instead. It was a practical decision, driven by the realities of survival in an uncertain world. That decision set in motion one of the most extraordinary examples of human-driven genetic change in the fossil record. A mutation spread. A food system was built, and civilizations were shaped by it. Heck, the word for wealth in multiple ancient language traces back to the word for cattle. We are the descendants of the people who could use that milk. Some of us anyway. Others of us are descendants of people who found other solutions to the same nutritional problems. Both are valid human strategies. Both produced cultures that survived. Drink the milk that works for your body. Drink it whole, and know the extraordinary story of how it got into your glass. Drink accordingly. Well, that's episode 11, the first episode of our 4-part dairy series on Eat or Die stories from the human table. I'm Zach Sykes, Renegade Health Group. Next episode, butter. The simplest transformation in dairy. Nothing but cream and agitation, and one of the most culturally rich and nutritionally rehabilitated food in the modern diet. We cover the history from ancient Ireland's bog butter to the French culinary tradition to the great margarine catastrophe of the 20th century. And we make the fat case fully and without apology. Find us on Facebook or Instagram at Renegade Health Group. Share this episode with someone who is still drinking skim milk because they think it's healthier. Help them. And leave a review. We are genuinely grateful for everyone, and they help people find the show. Until then, drink whole. Try A2 if you need to, and we'll see you for butter.